Let's start that. Okay, so we're going to start on our Chapter 14 notes. I have listed some of the definitions just here for you, so you don't have to waste your time writing them down. So we know how important random is, but random is an outcome that you cannot anticipate. Okay, you don't know what the next flip on my coin will result in. However, the long run relative frequency actually is consistent and predictable. So in the long run, what proportion of the times will I get heads on my coin? 50%, and 50% I'll get tails. Okay, so see, the long run relative frequency actually is consistent and predictable. Okay, and that leads us to actually what the probability is that long run frequency of an event, how the probability of that in the long time. We know that the sum of all the probabilities is 1. Okay, so that's something standard that we know. But let's talk about the complement of an event. So the complement of an event is 1 minus the probability that that event will occur. So I want to give you an example of notation-wise how that might work also. So if you said the probability of A happening is 0.2. Okay, so the probability of getting an A is 0.2. Then the probability of A complement, and you write that with a little c up there. Is this page crooked? No, okay. The probability of A with a little c, that's the complement. What would that value be? 0.8. Okay, it's the other part. So if getting an A is 0.2, then 0.8, do not get an A. All right, next, let's talk about some vocabulary, independent and disjoint. Independent is the same independent that you already know and love and have a song to. So, independent, independent, independent. When the, what is it? Good. The fact that you are one thing does not change the rate. Okay, so we know that those are independent if one thing happening isn't changing the probability of the next, okay? And so I want to give you an example. Let's say that we pick a card. So before we move on, let me do a quick what's in a card deck mini little lesson. So what's in a card deck? Okay, we have 4 suits, and they are hearts and diamonds and spades. Okay, and I should draw this one. Those are actually black. Here, let me put that in black. Okay, so then we got the spades, and then we got the clubs. Okay, very good. So how many is in each one of these suits? That is so sad. Okay. There is actually 13 in each suit. Okay. Wow. I can actually draw better than that, for real. Okay, see, let's try that again. And that's actually still not beautiful, but it's better. Kind of looks like somebody's not happy with me. Okay, and then we got 13 and 13 here. So for a total of how many items? 52 in the deck. How many of each color? 26 black and 26 red. All right, so there's your little mini lesson. And then, you know, your cards are 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King, and Ace. So that's your 13 in each suit. So let's say I have a deck of cards here, and you pick a card, and you give it back to me without looking. And I say, okay, I want you to bet as to whether or not the card you just gave me is red. Okay? So what's the probability that you will be correct? 50%, because, or 1/2, because half of them are red. Okay? I say, okay, cool, no problem. Hey, I'm going to give you another hint. Okay, you ready? I'm going to look at your card, and I'll give you a hint. So I'm going to look at your card. Okay? Here's your hint. And then you can see if you want to change your decision. It's an ace. Okay? So what's the probability that it's red now? It's still 50% because there's 2 black aces and 2 red aces. So the fact that I know it's an ace does not change the probability that it is red. Okay? So therefore, probability of red and probability of being an ace are independent events because the fact that you know one of them is not changing the probability of the other. Okay? The probabilities did not change. Okay, now, so that's independent. We're all good. We know independent. We've dealt with that this year already. One thing that is new idea is this vocabulary word of disjoint. Disjoint events are ones that actually cannot happen at the same time. With independent, you could pick a red ace, but disjoint events, they cannot occur at the same time. If one of them happens, then the other one does not happen. Okay? There is no overlap. So, for example, you're going to pick a card and hand it to me, and I'm going to say, what's the probability it's red? And you say, 1/2. And I say, okay, I'm going to give you a hint. Are you ready? Here it goes. I'm going to look at your card, and I'm going to say, guess what? It's a spade. And so what are you going to say now? It's what? There's a 0% chance that it is red because now that you told me it's a spade, you know it is black. So the probability of being red just went from 1/2 down to 0. The probability just changed. If the probability changes, then, so let me find where I am here. So the probability just changed from 1/2 to 0. So red and spade are disjoint events, and they cannot occur at the same time, and they are not independent. So here's the main idea that I want to make sure that you get, and it is that disjoint events are not independent. Disjoint events are not independent because with a disjoint event, telling you one thing changes the probability then of the occurrence. Yes, ma'am. Okay, so then that wouldn't be disjoint events because those things could still happen at the same time. Red and not a heart could still happen. So that's not disjoint. Disjoint events have to be separate items that can't happen at the same time. All right. So now let's draw some pictures here of what a disjoint event looks like. So let's get a visual representation. Since disjoint events cannot occur at the same time, my circles do not overlap. And that's supposed to be a circle. So let's say we have spade and we have red. Those do not have any overlapping cards. Okay? So in summary, disjoint events have no outcomes in common. Okay? Not disjoint events means that they do have some outcomes in common. So how would my circles look there? Yep, a Venn diagram that overlaps. So that would be like if I have an ace and then I've got red. I know that I have some red aces. So there are some outcomes in common. All right. Now, with disjoint events, we're particularly interested in how do you add these probabilities together. Okay? So, for example, let's kind of put our numbers in our spades. How many do we have? 13. In our reds, we have 26. So, if I'm interested in the probability of having a spade plus the probability of having a red, then how will I get that for disjoint events? So, yeah, we would have the chance of having a spade is 13 out of 52. And because there's no overlap here, I can just straight up add together my 26 out of 52 with it. So that means if I want to ask you what's the probability of having a spade or a red, then that would be 39 out of 52 because they just straight up add together. A spade or a red is the 39 out of 52. But now let's evaluate our numbers here in our non-disjoint events. How many aces are red? Start in the center here. There are 2 red aces. So out here on the side in the ace circle, how many aces are not red? 2. Okay. See, so you can see that this total ace circle contains 4 aces, 2 of which are in the red section as well. Okay. How many reds are there that are not accounted for in the middle? 24. Good. So there's a total of 26 in this red circle, 2 of which are also in the center. Okay. So the situation is, if I ask you to go the probability of ace plus the probability of red, then I could have some problems if you don't understand that there is overlap. For example, aces, there's 4 out of 52, plus reds is 26 out of 52. Okay, well, let me demonstrate what I just did there. I just added the aces plus the reds, and what happened? The middle section got double counted. When I added 4 aces plus 26 reds, my middle section got double counted. So I have to be aware of that, and I have to account for that by coming over here and subtracting away that portion that got double counted that are the red aces. Okay, that's that intersection that I'm going to have to subtract away, which are those 2 red aces that got double counted, and so that ends up being 28 over 52, which reduces to whatever, I don't know. Okay? All right. So do be aware, if they give you total values and there's overlap, you have to be aware, you have to make sure you do not double count that overlap. Okay, so that's disjoint and independent, and then the addition rule there. So now let's do union notation and intersection notation. All right? So union notation happens whenever you are doing the addition rules. Okay? If it's a word problem, they'll ask you, what's the probability of being a spade or a red? So it's that or word. Union is that or word in which addition is taken into account. It also could be not just or, but make sure you also count the middle section as well. So it's either or and both. Okay? Just like we have up here with the ace and the red. So this ace and the red, but also the red aces. Either ace or red or both. Okay? So sometimes people think it's not the both. They think ace or red means only ace and only red, and that's not true. Or implies or both also. Okay? All right. So the notation for this is a nice big U. So that's convenient that it's the union and its notation is a U. So the way it would be written is if I say I want the probability of a spade union red, then I know that amount was 39 out of 52. Okay? Could also do that. Probability of ace union red, which is the one up above it, is 28 over 52. Okay? All right. Now, intersection. Intersection is typically, well, that's a lot of times used with multiplication to find the intersection of items. If it was a word problem, they would be asking you, I want this and that to happen simultaneously. The intersection is when they are happening simultaneously. I want this and that to be happening at the same time, and that, of course, is when there is the overlap. Okay? So, the notation for that is the upside down union, and it looks like this. Okay? Now, I'm a visual person, so when I was back in school, I was like, ooh, okay, I'm going to do it over here to the side so I don't mess up that. I thought, okay, here's my thing, and then so I could remember it, I would come over here and I'd go, okay, that's the and. So I could always remember that that was the ands. Okay? All right. So with our intersection notation, then that would be something like us saying the probability of spade and red. What would that be? What is the intersection? What? 0. Good, because there is no overlap with a spade and a red because they are disjoint. Okay, let's do the other one. Probability of ace and red is how much? 2 out of 52. Very good, because there were 2 red aces. All right, now we have one final thing to do here, and I want a visual representation of union versus intersection. Okay? So I want you to draw 2 sets of overlapping circles, and I want you to label one of them union and one of them intersection. Okay? And now we're going to color in the portions of those that are represented by those words. So what portion of these circles on the left are represented by the union of them? All of it. So all of what's in there, this is the union. Joining together, union. Okay? What portion of these other circles is represented by the intersection? Just that middle. Good. Okay. Very good. I forgot that there was one other term that you might hear instead of disjoint that I wanted to let you know about. And so disjoint events are sometimes called, oops, that's not what I meant to do. They are sometimes called mutually exclusive. So mutually exclusive. Have you ever heard of mutually exclusive? Like if you're exclusive with your boyfriend or your girlfriend, then you don't go out with other people, right? So there's no overlap with your boyfriend and other boys. You're separate. Okay? As far as you going out with them. I don't know. You're exclusive, right? Okay. We hope. All right. I don't know. I'm just trying to come up with a way to remember it, and there you go. All right. Next. Two are independent events and finding their intersection or the occurrence of both of them at the same time. This chapter 14 is all about independent events, and you've done these before. You've done these kinds of problems of this independent multiplication probably since about 7th or 8th grade. I don't remember exactly when it gets introduced. But when we get back from Thanksgiving, we start having the more difficult ones. They are not necessarily independent, and so it kind of gets all a little bit more involved. And so then that's whenever it gets really hefty into a college level class and not just what you've learned in high school. So here you've done this before. Probability of 2 events happening that are independent is simply multiplying the probability of one event times the probability of the other event. So right here at first, when the events are independent, it's nice and simple. Multiply one probability times the other. So in this case, find the probability of flipping a coin and getting 2 heads in a row would just be the probability of getting a heads times the probability of getting another heads. Now, mentally thinking about independence, if you know that whatever you got on the first one, is that changing the probability of you getting heads on the second one? No, they are independent events. What you get on the first has nothing to do with what you're going to get on the second. So what's our numbers here? Half times half, and so we know that the probability of flipping 2 coins and getting heads is 1/4. Okay? Now, sample space of the 2 coins is the list of all possible outcomes. So when I picked this type of problem for a reason, because it's pretty basic, sample space, not very involved. So let's list all the possible outcomes for 2 coins. Heads, heads. What else? Heads, tails. Tails, heads. And tails, tails. So there are 4 possible outcomes that can occur. And in this case, how many of them get heads twice in a row? 1. So 1 out of 4 is, again, how you can see that 1 out of all of the possibilities is out of 4 possibilities. Okay, now, I use that to lead into this next probability. This next probability I don't think you've seen before, but it's pretty straightforward, and if you can remember the rule, then it's easy. So it does rhyme. So the probability of getting at least 1 is best figured out by going 1 minus the probability of none. So the probability of at least 1 is 1 minus the probability of none. And so I want to kind of demonstrate why that is, and I'm going to do that first with listing the sample space for the 2 coins again. So let's do that with, we got our heads, heads, our heads, tails, our tails, heads, and then our tails, tails. Okay. So this problem says, find the probability of flipping a coin twice and getting at least 1 heads. So I want to circle how many of these in the sample space are at least 1 heads. How many of them are there? There are these 3 sections out of the 4. Okay? Those 3 sections out of the 4 have at least 1 heads in them. So that's pretty simple. This was easy to figure out with the sample space because this sample space was this small. But I want you to look at the next example. In the next example, you are flipping 5 coins. So I'd like for you to consider how the sample space of this might look. You don't have to write it down, but I'm going to start and show you how out of hand it gets very quickly. So that would mean you could go heads, tails, 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 heads, tails, 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 heads, tails, tails, and so on. Tails, tails, heads, tails. Okay, I'm not even done with the ones yet. 1 heads. I'm not even finished with 1 heads yet. Tails, 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 heads. Okay, there's the 5 different ways you can have 1 heads out of those 5 coins. And then I need to do all the combinations of which you can have 2 heads, and then 3 heads, and then 4 heads, and then 5 heads. Okay, and then no heads. Okay, I forgot about that one. So, do you see how it gets to be very large very quickly? In fact, I won't tell you this right now, but there are 32 combinations in this section. Okay? You would have had to have written all that sample space out. That is why this is a better method to use this rule. It's everything except the one item that it is not. It's everything else except for no heads. All right? So let's mathematically do that here. Probability of flipping a coin twice and getting at least 1 heads is 1 minus the probability of no heads on the 2 coins. Okay? So, and this is pretty straightforward. If there are no heads, then they are both what? Okay? So I'm getting 1 minus probability of tails and another tails. So, and I write out everything on this. Normally I wouldn't write everything out, but I'm just showing you it all because of notes. So that is my 1 minus my 1/4. And ta-da, guess what that is? Okay? So it's kind of like it's the flip side. Instead of counting up all of the ways that you can have at least one heads, you just take 100% and subtract off that one way you don't. So that's what we're going to do here. Instead of doing all the different combinations, the best way is to do it this way. 1 minus the probability of none. And it's none what? None of the 5 coins are heads. Okay. So instead of counting up all the ways that there is at least one, I'm going to do everything minus the probability that none of them are heads. So that's 1 minus the probability. What does that mean? All 5 of them are tails. Okay? And of course you don't have to write all of that out. I think you can see that that's 1 minus. Would it freak you out if I go 1/2 to the 5th power? Because that's going to be a half times a half times a half times a half times a half for all 5 coins. Okay? And that ends up being 31 out of 32. Because 1/2 to the 5th power is 1 over 32. So when I subtract that, that's what you get. Okay? Do you see how it's easier to do 1 minus the probability of none rather than add up all of the 32 combinations? Okay, that's the purpose. So I want you to take a moment and try numbers 1 and 2 on your own. All right, well then let's talk about it. So all I have is just kind of like some hints drawn there. So that first one says, what's the probability of scoring a total of 18 when you roll 3 die? So my little blanks here represent rolling a die, rolling another die, and rolling another die. So I need the first one. All 3 of them have to be a 6 in order to get a sum of 18. Okay? Right. So what's the probability that this first one is a 6? 1/6. What's the probability that the second one is a 6? 1/6. What's the probability that the third one is a 6? 1/6. So if I multiply 1/6 and 1/6 and 1/6, then I get 1 out of 216, whatever that decimal is, I don't know. I a lot of times I mostly leave my probabilities like this in fractions because it kind of is a way of showing the work and showing where those came from. Okay. So this next one says, what's the probability of rolling 3 die and having at least one of them? My brain would go ding, 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 ding. At least one is 1 minus probability of none. Okay? At least one of them shows a 5. So I go, okay, then I need to do 1 minus the probability of none of the 3 dice showing a 5. Okay? So, how does a die not show a 5? 5/6 of the faces are not a 5. 5/6 of the faces are not a 5. And on the third dice, 5/6 of the faces are not a 5. So that means I'm going to do 1 minus that product of 125 over 216. Okay? Now, do you all know your math fraction on your calculator, how handy that is? So let me go ahead and show that to you in case you're not experienced with that. Now, I always tell my bridge kids to always put fractions in parentheses, because then you don't have to worry or think about the order of operations. So I just go 1 minus, and then some people's calculators automatically do the fractions. If it doesn't, then they have to do it. I tell them to make sure it's in parentheses, and so then I get an enter, and I get a strange messed up decimal. So I'm going to go hit the math button, and fraction is the first option. So it's going to turn my answer into a fraction, and that is nice 91 over 216. I don't know how nice that is, but it at least puts it into a fraction for you. Okie dokie. All right. After I went over those then, did it make sense better? Okay. Sometimes you're kind of like, you're not quite there. Let's see if you are better now. Try pages 3, or problems 3, 4, and 5. What time do we get out of here? Okay. So, yeah, go ahead and try number 3. I can probably give you the answers on that. 4, C, and D might be a little tricky. But I want you to, these are just notes, but I really would like for you to try them on your own first, and then we'll check them first thing tomorrow. So you technically don't have homework, except for I kind of want you to attempt all of these on your own before we go over. But I bet I can go over this one. I'm going to come around and give you your test grade while you are working.